3, 2, 1, go. We're live. This is Retraice segment number 72 for Tuesday, December 6th, 2022 at 11 p.m. Eastern, 8 p.m. Pacific. Retrace is about what's going on out there. The short answer that is computer control. The long answer is not going to come in this breath. Retrace is for outsiders. But we came to the conclusion that outsiders are not players, and the computer control game is player-oriented, so we're learning to be players. Maybe that means autodidactic artificial intelligence engineers. Maybe it means something else. Doesn't matter. We're in the math zone. We're in the math. Be in the math. Be of the math. Why? Look, we're going to study AIMA4e, Artificial Intelligence, A Modern Approach, 4th edition, Russell and Norvig, January to June inclusive, 2023. This is December inclusive, 2022. What are we going to do first? Front load the math, front load the code, get our hands dirty, get our brains fried, so that when the time comes, we can relax and enjoy our AI textbook. Sound good? That's what we're doing. That's what we're up to. You should be up to speed after that little shtick. Okay, we are working on pages circa 120 of AIMA4e. Why? Because that's the second place where we saw some math that might give us some trouble. Let's take it on. Let's wrestle it to the ground so it doesn't give us any trouble. Where are we at? So we are trying to solve a toy problem. You've got Romania. Just pretend like you've got Romania in your hands, on your fingertips, really. Each city is like a fingertip of Romania. I think I said that correctly, right? You want to put 3 airports amongst these cities in Romania, and you want to find the perfect combination of locations, etc., so that everybody's happy with their airport commute. We're not taking into consideration traffic or any of the other hillocks. We are taking into consideration hillocks, but not during your commute to your Romanian airport to be built. We haven't built the airports yet. Why do we care about toy problems? Go back to the last segment. We talk about how, and I put in the notes, I said in the notes, you know, a little bit of imagination. You can see how if we can find a way of making a problem like this tractable, it generalizes to a lot of other kinds of problems that are more interesting than our toy problem. And then I thought, I can't rattle off an example. And then I came up with a couple. First, you need to drop some emergency supplies. You only have 3 pallets. Refugees, there's been a hurricane or some other disaster, and you want to get as many of them as you want to be fair to everybody who's going to be in the drop zone. Those are our airports. You drop these pallets amongst all of the locations of the different refugees or camps or whatever it is. That was the first thing I came up with. It was actually the second one. I needed a lighter one. The first generalization, the first similar problem that I came up with, I don't know, this is just where my mind goes, was you got a bunch of enemy locations, enemy encampments, and you've only got 3 missiles to launch at them. Pew, pew, pew. Where do you land them so that you kill as many as possible? Sorry, that's just what I thought of. Toy problem generalizes to real world, more interesting problems. Okay, so that's why we work on a Romanian airport configuration. We have a system for dealing with technical stuff here at Retraice as of a couple of segments ago, ECMP. You start in English, yap, yap, yap. You switch then to code, typa. Then you switch to math, scribba. And finally, you want to take all that work and do something with it, go into progress, P for progress, take it out in the world and do something interesting. That's our little loop that we're using. It doesn't have to go in that order. It can go back and forth. You can do 2 things at the same time. You can skip a step, whatever. But that's the general idea that we came up with on page 48. And now we're applying it here to page 120 and Romania and their airports. There's soon to be airports. They don't have them there yet, not until we finish the problem. We're in the math stage. There's no actual code devoted by Russell and Norvig, a pseudocode devoted to this problem by Russell and Norvig. We're going to get to that, but we have to really, this is realness, this math, okay? So let's see what we're talking about. Where are we at? What's scary? Oh my gosh, what the hell is that? Okay, everybody just calm down. Just relax. Okay, I shouldn't have shown you that. You know, it's making me trip over my words. It's so scary. All right, let's start from the top to the bottom. We've talked about the top 3, and the new one is the one at the bottom, okay? So the first one represents, we'll call it the solution vector. What is a vector? Okay. You should be very careful with the word vector. Because if someone's going to, look, what people are going to do, if you go out on the streets by yourself without some sort of company, without someone looking after you, your favorite podcaster might be good, but I'm not available most of the time. You go out on the streets and start asking people about vectors, they're going to tell you that a vector is a mathematical object that has position and magnitude. Okay? So it's like a little dot, and it has, or direction and magnitude. And that's wrong. Okay, the strict mathematical definition of a vector does not require the idea of direction or position or magnitude. It is an ordered list in a certain kind of mathematical space or field. Doesn't matter. We're not going to get into the strict definition. The point is, don't get stuck on the word vector, and especially the physics interpretation of it, the direction and magnitude. If you do that, then you're not going to be able to understand when we talk about our vector, which is a bunch of airport locations. Okay, our vector has no direction and magnitude in it. It has x1 and y1, which is the location of our first airport, x2 and y2, which is the location of our second airport, and x3 and y3. These are x, y coordinates. Go to Retraice notes 71, I think is, I don't know. You got to Google XY coordinates, Cartesian coordinates. You got to do that on your own. I'm not doing that for you. Okay. But these represent positions of our airports, like proposed positions. These aren't actual numbers. One of the things that you're going to notice when you see the big scary pile, and maybe you're not scared by it, good for you, but a lot of people are. The big scary pile here is that we talk at Retraice about getting things, treating our hypotheses as a pile of numbers. Okay, we've talked about that in the past. You can find that phrase recurring in Retraice segments. There are no numbers there. Do you see numbers here? There's not the only numbers are the subscripts on the what we call the independent variables, the x and y coordinates of the three different. Okay, we want to get this ultimately into, we want to start with a pile of numbers, we want to use mathematics, and then we want to end up with a number. But right now, all I see is symbols, right? Mostly letters and then a couple of things we don't recognize. Okay, our first pile of numbers is here, but we're just representing the algebra of those numbers. So we're not going to actually give, when we just start talking about how to think about our solution, what does our solution look like? What's the shape of it? It's this. It's a vector, remember. A vector is just a pile of numbers. The order matters, and a couple other things matter, but for our purposes, it's just a pile of numbers, 3 sets of 2 numbers, okay? This is our solution vector. It's bold. Notice this x is thicker than this x, okay? That's significant. Don't mistake the two. It's actually a different color. If you look, I'm running out of colors. I mean, look at this. It's like Candy Crush over here, okay? I'm running out of colors, so some of these colors are a bit too close to each other. There's nothing I can do. It's your eye's fault, and it's nature's fault. It's physics. It's the nature of the universe. It's not my fault. This is thicker than this x. It's a little bit different font. Okay, this represents a vector. Put an equal sign, and we say that this x vector has 6 variables, okay? This is a 6-dimensional, or we're talking about a 6-dimensional solution, because you got to have the x position and the y position of 3 different cities, okay? So when we talk about our solution, at the end of the day, when all is said and done and Romania has its airports, how did we deliver those airports? We want to find the best vector x, that is the set of those 6 coordinates. But any set of 6 coordinates is a solution, as long as they're within Romania, okay? But we want to find the best one, and that's why we're going to have to do a little bit more math. Okay, what's this? What's this f of the vector x equals f of, okay, so all we're doing is just a little bit of expansion here, right? You put this here, now we got a function of x. It's a function is a mapping, what's a mapping? If you have a mathematical relationship between two spaces of or sets of ordered lists, which is what we're dealing with when we deal with vectors and matrices, and if the mapping is such that when you from the starting, let's do your left right. So we start from here, and via this magical invisible relationship, we can take any one of these ordered lists and connect it to, or point to, or arrive at another ordered list in the second space of ordered lists, and that there's only one that it points to, that none of these point to 2 different outputs over here. None of these inputs point to 2 different outputs over here. You're talking about a function, okay? That's we're not going to define it more strictly than that for right now. So we're talking about a mapping here, a function that takes x and then it points to something else. Now over here, it kind of seems like we're just saying the same thing again, and in a sense we are. But what you should always think about whenever you see f of x, f of anything, okay, it doesn't have to be a vector. It could be just a scalar like a normal x, or the f of 2. If you've defined the function algebraically, you know what to do with the input. It's kind of like a machine, an input-output machine, but math is not. There are no machines in math. Okay, we describe static relationships. That's all you can do when you draw these things is describe static relationships. The machines come in when we use computers, or you can use and computer can be a broad term. It doesn't have to be electronic. What you should think of when you see f of x or f of anything or g of x or g prime of x, you should think of something low. These are your independent variables. If it's just a simple one-dimensional univariate functional situation, then you're just going to have a line, and that's your x-axis, and each one of the little dots that make up that line, and there are infinitely many, can be an input to your function, okay, input to this magic relationship. What does it do? Okay, when you go to that point on the x-axis, put that into your function, boom, it pushes it up into the sky, okay, pushes it up. You should think of the function itself being the thing that pushes the input number, the independent variable, the x value in an xy coordinate system. I should do it so that you can left to right, because that's how you're going to be seeing it. Takes the input, which is an x number, let's say the number 2 on the x-axis, and pushes it up to 4. Why does it push it up to 4? Because f of x equals x squared. Okay, so if it takes input 2 and f of x equals x squared, the function is f of x takes the input x and the output is x squared, then it's going to push it up to 4. If it takes the input of 3, it's going to push it up to 9. It takes the input of 4, it's going to push it up to 16, etc. And eventually, what I'm describing is a parabola, and if you go into the negative numbers, it goes up again, because if you multiply two negative numbers by the rules that we've agreed to, you start going up again. But it doesn't matter. Think of functions as being the magic little thing that takes the x-axis and pushes it up. Now, it doesn't have to push it up. It can push it down, but it can't push it side to side. That's the point, okay? The function pushes it up. Here's the cool thing. You don't have to just limit yourself to one push-up axis. You can do 2. So instead of a line, you have a surface, and then f of x comma z, or f of x comma y, then you're taking 2 inputs and pushing them up to a number. And you can keep going like that. You can't picture it much further than 2. You actually can't picture it beyond 2, because that's a 3-dimensional space. You've got your 2 input dimensions, and then you've got your function dimension, which is the vertical, like say x, y, and z axes or something like that. How do you do a fourth one? There's no perpendicularity, but you can do the math on it. You can take as many independent variables as you want. If the function will take them, if the relationship holds between all those independent variables and one output, then you can do the math on it, okay? So that's just an introduction to functions of more than one variable, and that's what we're dealing with here. This is a function of 6 variables, a function of 6 independent variables. You can't picture all these things being on axes, but these things push this number up, and they can push it down. They can push it into the negative. It depends on what the function is. But in our case, what's not drawn here, or what's not written here, and I should have put this equation right here. I knew I should. No, I didn't know I should have. I would have done it if I knew, but I knew I was going to be missing something. Right here is our little rule that tells us exactly what arithmetic to do with that f. Okay, this is from yesterday's notes. This is the closest thing I have at the ready. It's a sum of squares function. Okay, so it takes the distance of each city to its nearest airport and squares it and adds all those numbers together, and we want that number to be as low as possible. Okay, that's what this function does. That's all this magic that's in this f that's not being written here is really based on that. That's our, okay, and we call it the objective function. This is our objective. Our objective is to minimize this value. So we want, when we put all these independent variables into the function and we get our output, we want our output to be as low as possible. In the simplest version of this, man, I keep clicking on. In the simplest version of this problem, you've got one airport in the middle, a city on each end. The input is the, well, I don't have coordinate inputs here, but we're taking the distance is 10 here, 10 here. Those are actually the inputs to the function. And we get 200 is good here. This is the best solution here. I think I'm saying this correctly. I might have just stumbled on something, but stay with me. And then if we put the airport here, it's not so good because it's much closer to one city and our little objective function properly captures that worseness in making the score go too high. We want to minimize the score. Okay? So that's what's going on here with this f of x. It's taking in all these things and then it's calculating the distances to figure out how good is our solution. How good are these airport locations? That's what the function tells us. Now, at that point, you can just move them around and keep trying different locations and just see if you can do it. But remember, like we showed the graphic of the locations of the cities, the Romanian cities, according to Russell and Norvig's figure. It's kind of hard to know where to put airports. Just looking at it, it's not obvious, okay? I'm not going to pull it up, but it's in yesterday's notes, and you can go to links.retrace.com. You can get to it pretty quickly. Okay, so what do we do if it's not so obvious where to put these three cities? What coordinates to use for the three airports? What coordinates to use? Well, that's where our big equation comes in. It turns out that there's a way of using calculus, because we're talking about a continuous space, so it's only a matter of, I mean, any position is okay. It's not discrete. Otherwise, we'd be doing something slightly different. We can put these airports anywhere on our map. The gradient of f, gradient of the function f, which is a vector. This gradient is a vector. Remember, just a pile of ordered numbers, an ordered list of numbers, a vector that has 6 dimensions. Okay, the vector has whatever this is, whatever this is, whatever this is, whatever this is. Okay, these are not the same as the coordinates. The coordinates are the coordinates. Okay, what we're doing here is some funny business. We're doing whatever this df dx sub 1, etc., df dy sub 1. Okay, the way we say this fraction is the partial derivative of f with respect to x1, the independent variable x1. Okay, now what is a partial derivative? A partial derivative is part of the total gradient or the total steepness, shapiness of a function. You can think of it as like being a hill. A function in this many variables is sort of like a hill in space, but it's in 6-dimensional space, not 3-dimensional space. And the gradient, if you take one point on that hill, you can calculate the direction to go that will increase your elevation most quickly. That's what a gradient does. And in our case, we want to get to the top of a hill, but you kind of want to go down to the bottom of the hill. It's kind of, it's easier to think about the hills than going to the valleys. What we want to do is minimize our costs. So whatever the steepest direction is to go to increase our number, we want to go in the opposite one, because our particular problem is a cost minimizing problem, not a score maximizing problem. But it doesn't matter. The math is just multiply by -1 and you get the same situation. You can do the whole thing exactly the same. The math is the same. It's important to remember this point, okay, the point that is represented on this hill that we're imagining, okay, it's a 6-dimensional hill, and it is not anything to do with Romania. Okay, the x-y coordinates of the airports in Romania are normal, and we understand them. It's like putting pins on a map. We move them around, and maybe little strings connect to the cities. And this is not that. This is not the gradient of that map. And these 6 partial derivatives are nothing to do, well, they're not nothing to do, but they are not part of that world. They are in a mathematical world, a 6-dimensional mathematical world, where they all together amount to a single point in that 6-dimensional space. And what we're asking when we apply the del operator, the gradient operator, to get to arrive at a vector about that point, that is not the same as the input point. Our input is the result of the function, okay? So first we take our 6 variables, put them into the function, then it turns into a number by itself, and then we take that number and in this form, and we apply a gradient operator to it. What we're getting is a 6-dimensional vector, okay, 1, 2, 3, 4, 5, 6, of new numbers. And what these new numbers do is they tell us this very hard to imagine situation where we're in the 6-dimensional space. How do we go uphill? How do we go? It's easy to imagine going uphill in a 3-dimensional space. Going uphill in a 6-dimensional space is mathematically essentially the same. You just have to let go of being able to visualize everything no matter what. Okay, so the gradient helps us go uphill. We talked about how the limit of the gradient is basically it only works locally. So you make a guess. You start with a guess. Let's say whatever numbers we want to plug in for our coordinates. We apply the objective function to our guess, and out comes a number. We apply the gradient to that number in this form, and or to our guess, not to the number. We apply to our guesses, our collective guess here of 6 things, and we get these 6 numbers, and that will tell us the grade or the gradient of that particular guess in the solution space, and then we know how to improve it locally. But as we've discussed, it doesn't help us if we start on a hill and we want to go to a bigger hill by going downhill first. There are other methods for that. It gets more complicated. We're just dealing with the mathematics here. Focus on the mathematics. It will get us to the top of a hill or the bottom of a valley, wherever we start, once we have a guess. But it will not find it, so it'll find our local maximum or local minimum. It will not find the global maximum or global minimum. Okay. Now what? What the hell is this? How does that, the green thing and the F and how does that turn into a number? Well, it's a partial derivative, okay? And it turns out that a gradient is the generalization of a derivative, but it's the generalization of a total derivative, which is just the normal derivative in the beginnings of calculus. This is a partial derivative, and you put a bunch of them together, and they make up a total derivative in the form of a gradient. This is how you get there. So I know this is a lot of math, but this is the new math for today. I've tried to sort of walk through the equations that we've dealt with so far. Now we're going to just talk about a limit. I'm not going to exhaust it, but I want to give you a sense of how you turn this thing. And you have 6 of them that you have to do this. You have to turn this back into numbers. If we're not dealing with numbers, we're just dealing with symbols, we're dealing with fancy algebra, but we need, at the end of the day, we need numbers to tell us specifically what to do with our guess, okay? How do you turn this into numbers? What you do is you plug in your values here, okay? So in our case, we'd have x1, we're not using the y here because our first partial derivative does not have y in it, okay? So we add x1, we add our denominator h, and we calculate our objective function based on these inputs. And then we subtract it, so that's going to lead to a number that's different from just taking x. And then, gosh, where do I put in the y? I'll have to calculate this because this function wants a 6-dimensional input. We're holding one still. We're holding the y still. Anyway, I'm going to do the calculations tomorrow or tonight. And then we subtract it, and that's the difference. Ultimately, what you're getting here is a rate, okay? This is the fundamental idea of calculus, this idea that you can take a denominator and put it in the numerator, and you push that denominator closer and closer to the number 0, and you start to get an instantaneous rate. So if there's a curve and you're trying to figure out the rate at a point, you can use smaller and smaller rectangles until you get, you arrive at a limit You never arrive at the limit, but you use the idea of calculating smaller and smaller and smaller, smaller. Get the 2 points that you need to create a rate as close as possible, and there's never an end to it. You have to define that sequence into a series that amounts to an actual number, a rate like 2. 2 is 2 over 1. 2 y's for every 1 x. Okay, so you go to x, the rate. If your function is, if the rate of your function is 2, then for every unit on your x-axis that you move up 2 units on your y-axis. Okay. The point is, this partial derivative is going to end up being a number like 2 over 1 or 37 over 6 or 1 over 2 or whatever that is a rate. Okay? And we'll plug that normal number into the first place of our vector. And then we do that again 6 more times using this formula here. Okay? You know what? The reason that this one doesn't incorporate I already know the y's here is because the definition I got from a different book, and they weren't dealing with a 6-dimensional with y's. But we would definitely, this should be y1, and then x2, y2, x3, y3. That's what should be here. So just try and picture that, okay? Because the only one that we're going to hold still and not change is the x1. Okay. Okay, that's it. So we're gonna, it's gonna, talking about it is not as effective as actually calculating it. So we're gonna calculate tomorrow, and that's gonna get us back to our numbers. And then we're gonna have, instead of having all these fancy symbols, we're going to have just a gradient that has a bunch of numbers here. And then what do? I don't know yet. I've never done this. So this is the this is the notes from yesterday. Okay, Re72. So far, we've been looking at the notes that'll be in tonight's notes, Re72. These just, gathering all the equations and sort of labeling them properly. But I get to the point where, I want to, and see, this is wrong. I already know this is wrong. It's magnitude and direction, but this is the way people talk about it. We have to be able to turn these partial derivatives into numbers that are useful and that tell us which way to go with our solution. Once we give it a guess, we need to be able to prove it. I'm not there yet. I can't just rattle off an example, but that's where we're going to go with this. We have to bring it all the way back to, we started with a pile of numbers that we turn into a vector. Now we're using a bunch of algebra and calculus and vector calculus to structure how we're going to calculate our answer. But eventually we need to calculate an actual answer. We need to be able to take a guess, put it in, get a gradient out, improve the guess, and loop it like that. Okay? So that's what we're going to do as soon as I'm able to do it, which I think will be tomorrow. But you never know. All references will be in the PDF notes, retraice.com, retraice.com. You can get to the PDF notes in so many wonderful ways. You know what? Go to our website. Just do it. Who knows? Something good might happen to you. If you were there right now, loop it like that. You could listen to me talk, so that's what we're gonna do, while I'm also talking. As soon as I'm able you're to hearing do it, which I think right will be now. Tomorrow. I think. But what's he talking about? All references will be in the PDF. Oh, he's talking about the references. This show must be over. Okay, we've got other things like Margin, our little sister podcast in the background, notes up here, GitHub, blog. It's not much on that right now, but there's stuff there. Links.retrace.com is pretty cool, except clicking on it does nothing. What's that about? Why is that? Oh, that's broken. That's wrong. Okay, I'll fix it. But you can type in, it's easy to remember, links.retrace.com, and that takes you to useful links, and then you can get all our social media and all that stuff. Anyway, I want you to check out the website because it's actually got some useful stuff if you're doing this sort of stuff. All right, this has been segment number 72. Same time tomorrow, 11 p.m. Eastern, 8 p.m. Pacific. Could be segment number 73, and we will continue on our deep dive into the math. And eventually we're going to get to coding it and then taking it out into the world. Okay, signing off.